Hello everyone, I hope you all are doing well. Today, I will be presenting my research title AI powered medical imaging enhancing diagnostic accuracy in radiology. In this presentation, I want to draw your attention for all the contents that will be disclosed one by one. Let's come to the introduction. Medical imaging plays a vital role in detecting diseases like COVID-19 and pneumonia. However, the increasing volume of radiological data, diagnostic variability, and the shortage of trained radiologists make disease diagnostic challenging. Artificial intelligence and deep learning have greatly improved image-based diagnostic, but they still faces issues such as data quality, interpretability, and generalization. This research aims to overcome this limitation using hybrid deep learning approach. Let's move into the literature review. Several studies have used convolutional neural network or CNNs for thoracic disease classification. For example, Wang et al. Developed chest X-ray dataset for multiple disease. Raspurkar et al. Introduced ChexNet, which achieved radiologic level pneumonia. Other researchers like Apostolopoulos Oster applies transfer learning for COVID-19 and multi-class classification. Despite their success, CNNs have two key limitations. They fail to capture long-range spatial dependencies and lack of global contextual understanding. Recently, fusion transformer introduced by Dosovitsky et al. Have shown in strong potential capturing global image feature, outperforming traditional CNNs in many cases. The main problem identified in the study is that CNN-based models are effective but limited in modeling long-range spatial relationships. They also lack interpretability and struggles with generalization on limited medical datasets. Therefore, there is a need for a model that combines global spatial learning and sequential temporal learning to improve diagnostic accuracy. The existing literature, very few work, integrated vision transformer VIT with recurrent neural network RNN variant such as GRU, LSTM. Moreover, there has been exploration of how VIT patch embeddings can be modeled sequentially. Additionally, existing VIT or CNN-based models have rarely been evaluated on balanced COVID-19 datasets. To bridge this gap, my research compares three hybrid architects, VIT, RNN, VIT GRU, and VIT LSTM. This is the block diagram for the model that we are going to propose. Let's jump into the proposed methodology. This slide shows overall workflow of my proposed method. First, chest X-ray images were collected for three classes: COVID-19, pneumonia, and from various open datasets. All images were resized to 224x224 ratio, converted to RGB and normalized for consistent input. The dataset was then split into training and testing set. Next, features were extracted using pre-trained vision transformer, which divides each image into patches and learn global spatial relationship. The VIT feature embedding were passed to RNN, GRUs, and LSTM models capture sequential dependencies among patches. Finally, a softmax classifier predicted the class level and performance was evaluated using accuracy, precision, recall, and F1 score. The dataset used contains 6,939 balanced chest X-ray images equally distributed among the three classes COVID-19, pneumonia, and normal. All images were pre-processed, resized to 224, x224 size, converted to RGB, and then this processing ensures uniformity and eliminates dataset bias. These slides provide the proposed VIT LSTM model, which had gave the best performance. The vision transformer split each image into small patches and learn global spatial features through self-attention. These feature embeddings are then fed into an LSTM layer, which model the sequential relationship between patches. The LSTM output is passed through a fully connected softmax layer that classifies image as COVID-19, pneumonia, or normal. This hybrid architecture effectively merges VIT attention-based feature extracting with LSTM contextual learning, resulting in the higher diagnostic accuracy and better generalization, and then standalone the VIT model. The performance of each hybrid model was compared quantitatively. The VIT-LSM model achieved the highest accuracy of 96.67%, outperforming the VIT-RNN with 93%, VIT-GRU with 95.51%, and the baseline VIT with 95%. The precision, recall, and the F1 score were also high across all cases, particularly for COVID-19 detection, with a 97% recall rate. This result confirmed effectiveness of integrating VIT with sequential models medical imaging. This conclusion matrix have provided the class-wise performance of the model. You can observe that VIT-LSTM shows fewer misclassification compared to VIT-GRU. Most confusion occurs between pneumonia and other cases, as their visual patterns are quite similar. Overall, VIT-LSM demonstrates superior capability in identifying COVID-19 and pneumonia with high precisions. In conclusion, VIT-LSTM hybrid models effectively combines the attention-based extraction of VIT with temporal learning of LSTM, achieving the impressive 96.67% accuracy. This framework enhances diagnostic accuracy, interpretability, and clinical relevance. The future work will include fine-tuning the VIT layers, expanding the datasets with multi-institutional image, incorporating RSC and AUC analysis, and integrating explainable AI techniques like RadCam. Thank you for your attention. Have a nice day.